So, as I said in the introduction to the unit, a large part of the effort in my half of the unit, as you can see in the assignments, is in building up and manipulating these three-dimensional virtual environments. Okay? So you have seen in the later assignments, we have these things where we want you to construct, I'm over it maybe, to construct a village made out of simple kind of house or building type structures. And these are going to be built by, you constructing a 3D model of a certain basic type of building, and then by populating your environment by taking various copies of that building and moving them around in your environment, rescaling them, making them larger, changing, rotating them to change the orientation they have in the environment, maybe taking the reflections of them. If you've drawn a kind of a right-handed building, taking a reflection of it to generate a similar left-handed style building. So now we'll be discussing these things as we go through, but the mathematical techniques that are lying behind that is transformations of three-dimensional space, okay? Or more precisely, isometries of three-dimensional space. All those kinds of operations that I've mentioned, translations, shifting things around, rotations, reflections, they're all examples of what are called isometries, which are, we'll meet that formal definition later, distance preserving maps of three dimensions. So in order to build up to that, we're first going to start in the two-dimensional case. I'm going to give quite a thorough treatment of transformations in two dimensions. Okay. Okay. So that's what we're going to start with. Okay? So in all of this discussion, we'll use the word transformation to refer to any function of the plane to itself. Okay? Purposes of this plane. Of course, okay, the plane is the geometric object, but of course we're describing it using vectors, position vectors of points in the plane. So we naturally think of the plane as a vector space, a system of vectors, and we have the vector operations of addition, scale, and multiplication. Now, of course, this is all familiar to you from the work we've been doing with Stephen and Matt's methods. So I don't know, you won't have seen the definition of linear transformation yet, but I think you saw it in your first year linear algebra. So we'll go through the definition now again. Since we're dealing with the vector space, the vector space has the structure of the two operations, addition and scalar multiplication. Well, the natural family of functions, or transformations to consider then on that space is the family that fits with the structure. And what it means to fit with the structure is when a function or transformation f has this property here, where given any two vectors a and b, the fundamental kind of transformation you can do with them is to take a linear combination in the vector space, alpha times a plus beta times b. And if your transformation f fits well with that operation, fitting well means that the value of f on the linear combination alpha a plus beta b is the corresponding linear combination of the individual values, f of a and f of b. That's what we mean by the linear transformation fitting well or preserving the vector space structure. It takes linear combinations of vectors and it sends them to linear combinations of the individual images of the vector. So any transformation, any function f from the plane to itself that satisfies that is called a linear transformation. The vector space type transformations. And more generally, you consider linear transformations from any vector space to any other. But we're just focusing on the plane, so we're just focusing on linear transformations from the plane to itself. Now, as you'll find in the maths methods, and which we need to use here, linear transformations are represented in the computer. They're represented for the purposes of calculations with them. They're represented as matrices, okay? Not by formulas necessarily inside the computer, but represented by matrices. So how is it that a matrix can represent a linear transformation? That's something that I want everybody to really appreciate, and really have a key understanding of, because it's the representation of these transformations by matrices underlies, you know, a huge proportion of the stuff that we're doing in this unit. So we need to be very, very clear on the strong connection between these transformations and the matrices. So how do the matrices arrive into the picture? Well, let's see that now. Focusing on the case of transformation from the plane to R2 to R2. Okay, we have this idea that we've got a standard basis of R2, the two vectors I and j. They're two unit vectors pointing in the positive direction of the x and y axis. I goes along the x-axis, j goes along, sorry, I goes along the x-axis, j goes along the y-axis. And we know that any vector v in the plane can be expressed as a linear combination. It's x coordinate plus y. The vector v is x times vector I plus y times vector. Okay, you're very familiar with that. Now, if f is a linear transformation, that immediately tells you that the value or the image of f, the image of v under f, the value of the linear transformation of v, because f is a linear transformation, it has to be x times f of I plus y times f of j. Okay, the two parameters there, x and y, they're both scalars. The x and y are playing the role of the alpha and beta in the definition of the linear transformation. So what that tells you is that it's enough to know f of I and f of j. Once you know f of I and f of j, all the values, all the images of the linear transformation f are determined. Because if the argument v is xi plus yj, then the image f of v has to be x times f of I plus y times f of j. So just knowing these two pieces of information, what f of I is and what f of j is, that determines the whole linear transformation. So that is, to know the vector f of x, it's enough to know the vectors f of I and f of j. To know the vector f of v. Anyway, so there's just those two pieces of information. Well, let's give a precise description of f of I and f of j. They themselves are two vectors in the plane. So f of I itself has a representation as a linear combination of I and j, and so as does f of j. We just give names to those coordinates or those components. So f of I we'll think is a times I plus b times j, and f of j is c times I plus d times j. We're just introducing names or labels for those components. And then if we put that together with what we've already got then, so here in the third equation from the bottom there, we've got f of v is x f of I plus y f of j. And we just take these two expressions for f of I and f of j and just substitute them. When you substitute them into that and collect together the i's and j's, we now have a representation for the image f of v as ax plus cy times I plus bx plus dy times j. So we see that the components of f and v is some kind of mixture of the components of v with the components of f of I and f of j. Some mixture in this first bracket here, mixture in the second bracket, and the ingredients going into the mixture, if you like, are the components of the argument v and the components of the images of the basis vectors I and j. The a, c, and the b and the d, they're the components of f of I and f of j. So that kind of gives us a good way to think about linear transformations. Once we know what happens to f of I, what happens to I and j, we know how the whole of f behaves. And it's this description which leads us naturally to the representation by matrices. But there's some subtle points here about exactly how the representation can work, and different ways of setting it up. The conventional way for us, or the convention we're going to establish for this unit, is to agree to express our vectors as column vectors. There's two choices. We can either agree to write out the components of a vector in a column or as a row. Now, for some sense, in some ways, writing out coordinates of points in a row is kind of more natural because it fits in a sentence easier. It doesn't force you to move the lines of text away from it. So you might think rows are better, but it's slightly more conventional, or slightly in more use to write, in this context, to write your coordinates as column vectors. Because if we agree to do that, and we just repeat the equation above, but now writing the vectors out as columns of their components. So I start off with f of v on the left. V we've decided is xi plus yj, so I'm talking about f of xy. So this expression here now, written as a column vector, becomes this column, ax plus cy over bx plus c. And this is where the definition of our matrix multiplication comes from. We just agree to write that. We agree to write that column vector in the middle, where cy over bx plus cy. We agree that that's going to be the definition of the product of those two products, that 2 by 2 matrix. This, if you like, is where the definition of matrix multiplication comes from. It's the rule for how to mush this 2 by 2 matrix into this column vector in order to give you this vector. And it's defined like that so that it produces the linear transformation. So this thing here we now recognize as the matrix product of the 2 by 2 matrix with the 2 by 1 matrix or column. And the matrix is determined by f of I and f of j. The first column is f of I, ai plus bj, that's f of I, and the second column, ci plus bj, that's. So what we say is, you'll be given this a full workout in mathematics with Steve, but we're just doing the bits we need. But what we say is that the matrix A represents the linear transformation. Now, in legal terms, you kind of have to add on this phrase with respect to the basis I and j. It's with the representation is with respect to a certain basis. Now, almost all the time we'll be using the standard basis I and j. If you were to use a different basis for the vector space, for the vector space R2, you get a different representation. But if the basis is fixed, then you have this exact correspondence. This is what I'm discussing here. There's an exact correspondence now between linear transformations, these functions of the vector space, and 2 by 2 matrices. They're two different things. One is a function, and the other is just a 2 by 2 square of numbers in the page. But in some senses, because there's this exact correspondence between them, they kind of coalesce in our minds. And we kind of think of a linear transformation is a matrix, in some sense. But every linear transformation F is represented by a unique matrix. And every 2 by 2 matrix represents a linear transformation. There's this exact marriage, one-to-one, with the two families of objects. The linear transformations on one hand and the matrices on the other. Okay. Now, we almost think of them as the same thing, linear transformation and its matrix. But we kind of, that might lead us astray. We kind of have to remember that they are formally two different types of objects. So when we need to be careful about the difference between the matrix as opposed to the linear transformation that it represents, we'll use this kind of notation. Lambda square bracket A. So A is a matrix, but lambda square bracket A is the linear transformation represented by the matrix A is just a 2 by 2 square of numbers. The lambda of A is a more abstract object. That's the function, linear transformation from R2 to R2. And this is the conventional way we're going to be describing and calculating the linear transformation. And that's how the little MATLAB programs that we write, that's how they're going to represent the linear transformations. But now there's nothing in the universe that tells you you have to write vectors as columns. Equally well, you could have chosen to write them as rows. Indeed, fitting it into English sentences, that's perhaps the best way. So maybe you might describe your vectors as row vectors. Well, if you just repeated what we've done there, then you'd be thinking of the linear transformation like this. F of B is f of the row vector xy. We've already agreed that that's ax plus cy, bx plus by, that row vector. Well, using the same, I mean, we want to keep the definition of matrix multiplication the same. You don't want to suddenly have two different types of matrix multiplication. Well, how do you produce that row vector? How do you produce this row vector here in the middle out of the row vector xy and the matrix, or some matrix using A, B, C, and D? Well, you have to do it like this. You have to have the row vector post-multiplied by the matrix. Previously, we had the column vector pre-multiplied by the matrix. Now we've got the row vector post-multiplied by the matrix. But it's not the same matrix we met before, is it? Before we had AC reading across the rows, we had A, C, B, D. Now we've got A, B, C, D. That is the transpose of the matrix A we have. So A is still representing this matrix here, but under the row representation, under the row vector representation, you're not multiplying B by, you're not doing the product A times B, you're doing the product B times A. Okay, so that leads us to this representation. A linear transformation is represented by post-multiplying the argument vector B, post-multiplying the matrix by the matrix A times. It's still a valid way of representing linear transformations, but it's different in its implementation. It's different in the technical detail. But why do we choose one over the other? I mean, as I said, the row vector representation would fit better with our paragraphs if we wanted to stick a vector in the middle of a sentence. But the reason we choose the column representation is it's purely arbitrary choice. The way the conventions are defined, the way matrix multiplication is defined, it ends up with that the matrix goes on the left of the argument. And I think the way I think about it is choosing the column representation, is putting the matrix on the left of the vector B replicates the normal way you write functions. Whereas if you were to choose the row representation, well, if you still wanted to use the convention of putting the function name to the left of the argument, then you're kind of doing the opposite thing in the convention. But of course, maybe I'm making the point a bit too much, but the choice of writing f of v with the function name to the left of the argument v, that itself is entirely arbitrary. I mean, why not write this as this? Why not write the function f applied to the argument v as the f on the right? I mean, it's purely arbitrary choice. We've kind of incorporated this into the way we read these things, f applied to v, and it kind of fits in with the direction of English, going left to right, but of course that's not unique. Other languages go right to left, so maybe that would be more natural. Languages or whatever. You know, these are all just arbitrary choices that they're just the way things have developed. This this type of notational system is called prefix. Where the function object goes to the left of the argument. That's prefix. And this would be postfix. Where the function, if you were to write the function then to the right. Now, in normal mathematics, you almost never see postfix. In some areas of computer science, where they're very close to the actual physical implementation of these ideas in computers and programming languages, I think you do encounter real examples of postfix notation being used. But in the normal way we discuss mathematics, we almost exclusively use prefix notation. Okay? And that tradition, so really it's just about competing traditions and competing choices that guides us to use in one way of describing the argument. So for that reason, we're going to agree, I hope, unless there's a few radical people in the audience, I think we should all agree to use the column representation. If you really want to be a stick in the mud, you could do all your assignments using the row representation. You'd have to be extremely careful about it, though, because you'd have to translate everything I discuss in the lectures. Well, what would you have to do? You'd not translate, you'd have to transpose everything I do in the lectures and turn all the columns into rows and vice versa. But that would still be a valid choice. What you shouldn't do, and what wouldn't be valid, would be to use a mixture of the two schemes in the one solution. You know, to start doing calculations, sometimes using row representation, sometimes using column representation. So then you're mixing. It's like speaking in two languages at once. It's perverse. It's just confusing for the listener or the reader. Okay? But there's nothing special about one or the other readings. It's just an arbitrary choice. It's just about tradition. Okay. So we have this idea that our linear transformations are represented by matrices. And this extends into the properties of matrices on the one hand and the properties of the transformations on the other. First of all, any questions just on what we've said so far? Or anything I can clarify? Okay. Well, so this representation is quite a rich idea. It isn't just that f applied to b can be calculated as a matrix times b. It also extends into the properties. And two key ways, or two of the most important ways the representation extends, is into the operations. So there's certain operations that can do with functions, and they are mirrored by certain operations to do with matrices. Okay, so it's to do with two most important ones are to do with composition and inverses. If you have two linear transformations f and g that are represented by matrices A and B respectively, then the composition, so composition of functions is a natural operation, f after g. The matrix that represents after g is exactly the matrix product A times B. Okay. But you have to get the order important. Composition f after g. G is the function that's applied first, and then f is applied to the result of g. And that's replicated in the matrix product in that A is the matrix on the left and B is the matrix on the right. Okay. G after f will be represented by matrix B times A. Secondly, an inverse matrices, an inverse transformation. If the linear transformation has an inverse, not all of them do, just as in exactly the same way as not all matrices do, but if the linear transformation is invertible, then its inverse is represented by the inverse matrix. Okay. So is there anything to prove here about in order to establish this? This is section 4.2. So point one about compositions, well, the proof kind of falls out of the notation, really. If you're applying the linear transformation f after g to a vector v, well, by definition of composition, that's just f of g of v. That's just the definition of circle, of composition. Well, under the matrix representation, then, if you want to do g of v, you have to do the matrix b times v. And if you want to do f of something, well, you have to take the something and multiply it on the left by a. And then it's just a matter of repositioning the brackets to say that this is exactly the same as the matrix product A times B itself multiplied by B. This is the definition of the representation. And this is by associativity of matrix multiplication. Matrix multiplication is associative. There we have three matrices. The third one is vector B. Those three matrices multiplied in that order, A, B, B. But associativity says that the order of evaluation does not make a difference. But then this equation we've shown says that if you want to apply f after g to something, you multiply it on the left by the matrix product. So that's exactly saying that AB represents f after g. So overall, this says that AB represents f after g. Similarly, with the inverses, if we have f of v as a vector u, then obviously v is f inverse of u, assuming the inverse exists. So that means that A times B is equal to the vector u. The matrix A is representing F. But then multiplying on both sides by the inverse of A, this is this representation here. So that says if you want to get F inverse of some argument u to get the vector v, you just multiply u on the left by A inverse. And so in other words, A inverse represents F inverse. Of course, we're assuming here that matrix multiplication is associative. And we're kind of assuming stuff here about the existence of the inverse matrices. I mean, the fact that the inverse linear transformation exists does imply that the inverse matrix exists. Theoretical, technical details lying behind that. But that kind of establishes the key part of the representation. Functions, these nice functions in terms of the vector space structure, functions that preserve the vector space structure, are in exact correspondence with the collection of matrices. So it's what allows us to implement the calculation of these functions into the computer. So the setup is just a system of operations with arrays of components in the computer. Okay, I'm going to leave it there for this morning. I think a few of you might have some individual questions people were trying to ask me at the end of the last time, so I'll stick around for a few minutes to deal with those. So you're submitting assignment 2 at the end of next week, and we'll continue our discussions working towards assignment 3 in the lectures, in the sessions next week as well. Okay.